Hi, my name is Tom Hebb, and I work on Red Team X at Meta. We do security research for external products, and you can find some of our blog posts at the URL here. Today, I'm going to be talking about how to analyze firmware in various pieces of hardware, this talk will be divided into 3 parts. This is the first of those parts, and make sure to check out the other 2 afterwards. Let's start at the beginning. What is firmware? There are a lot of different definitions you'll see, but for our purposes, firmware is any proprietary code that is running outside of the main OS. So it's not running inside Android or Windows or Linux as a process. It's running on some dedicated processor or in some non-OS environment on the same processor. This definition is the one we're using because it has 2 important properties. One, we are only talking about proprietary firmware because we're talking about reverse engineering here. There are a lot of firmwares that are open source or have a lot of extensive documentation and tooling, for example, UEFI. And while those are firmware, it isn't as useful to reverse them because you can just go and get the source code directly. And then we're talking about stuff that runs outside the main OS because likewise, binaries on Windows or Linux, if you want to analyze those, do static analysis or even dynamic analysis on them, there's a wealth of tooling and debuggers that let you do it pretty plug and play. What are some examples of firmware you might find? Things like this might come to mind. So these are dedicated devices, peripherals for your computer or phone that do run firmware. They sort of run firmware as their only code. There's no full operating system running on your keyboard, on your USB hub, on your SIM card. It's all just a very low-level piece of code running more or less directly on whatever processor is in there. But you can also find firmware in other places that you may not be as familiar with. This is firmware that runs alongside your OS. So this is on your phone, on your laptop, on basically any modern electronic device. You have huge amounts of firmware that are running things behind the scenes. One example of that is your Wi-Fi radio. Because Wi-Fi takes such a high amount of real-time processing and has gotten so complex over the years, there's really no way to handle all of that modulation, demodulation, decoding in the operating system itself. It would just be too slow and too complex. Things like your GPU run their own firmware for video decoding, for example. They know how to parse video and make frames from it. Your flash drives, SSDs, those all have firmware as well because flash memory is a pretty unforgiving and strange technology at the hardware level, and so to make it look like a traditional hard disk, you need a lot of processing, and that always happens in firmware, again, so that you and the OS programmer even don't have to care what's happening. Why are we talking about firmware in this set of security talks? It's because firmware is often very important from a security perspective. Firmware can do a lot of stuff and often lacks a lot of the protections that exist in a normal operating system. So while on Windows or Linux or Android, you have very robust protection mechanisms, security models, permissions, users, mitigations like ASLR, pointer integrity, all that kind of stuff that makes it harder to attack and exploit. Firmware is often written to a much lower standard, both because it is more bespoke and has less shared code and code review, and because it's just running at a much lower level. It's running generally just directly on top of hardware with no type of OS in between. And that makes it harder to implement some of those complex security mechanisms. If you can compromise a piece of firmware, you get a lot of access in many cases. And this slide is just representative. It's not authoritative for any of this, but it does show what you might expect for these different kinds of firmware from the last slide. So for example, if you get code that runs in the Wi-Fi firmware, you can potentially exploit that remotely because it handles packet data coming in from the outside world. If you're just sitting near someone's device and you can send them malicious Wi-Fi packets, you might be able to exploit a bug in the Wi-Fi firmware with no physical access needed. And then the Wi-Fi chips, because they move so much data back and forth, usually have direct access to at least some amount of the main system memory. And This has improved in recent years with things like IOMMUs, but in general, having that access opens up a whole avenue of attack vectors to you for getting into the main OS and getting to your whatever it is you want to target. I won't go through every item on this slide. They mostly speak for themselves, but some firmware can even damage hardware, for example. Like if you compromise the firmware on the power management IC in a phone or on the flash storage, you can brick that flash storage, make it stop working, write to it a whole bunch so that it has no writes left in it. You can up the voltage and fry the chips. So this can be very sensitive and very dangerous if firmware isn't properly protected. And since this is a bug bounty talk, I will be remiss to not talk about why else you want to target firmware, which is that we'll pay you for it. This is an excerpt of some of the payout guidelines that we have for our Reality Lab devices here at Meta. So that's Quest, our smart glasses, and our Portal devices, and perhaps more in the future. And you can see some of these goals, for example, secure boot bypass, require interacting with firmware. So secure boot is the chain of code that runs prior to the OS getting loaded. And so a lot of those bootloaders and the places where you would compromise the chain of trust to compromise secure boot are in firmware, and you need to be able to understand firmware to find bugs. And then some of these other ones don't require compromising firmware, but they do. They are very easy to get to if you do. For example, we have a microcontroller in Quest 2 that handles the camera timings, the camera indicator light, and brings a lot of sensor data in from the IMU and accelerometers and gyroscope and all of that to the main CPU. So if you can run code in that firmware, you get access to all that data, and then you have gotten direct access to system-level sensor data, as it says here. Hopefully that's convinced you why. So let's talk about the how. I'm going to break this general process up into 4 rough steps, and there's always a bit of overlap, but I think these are pretty well defined. The first 2, which we will talk about in this part of in this video, are enumerate and obtain. And enumerate means figure out what firmware exists on a device. So you're staring at this device, you know it runs Android or Linux, but you don't know what firmware is there because that's a lot less obvious. So how do you figure that out and then choose firmware that's interesting to you? Once you've chosen the firmware, you get to obtain. You need to figure out the location that that firmware actually lives and get a copy of it, because without a copy of it, you can't really analyze it and figure out what it does. The next 2, extract and analyze, we're going to cover in the next video. And I'll talk about them in more detail there, but basically, once you have the firmware image, it's usually not in a standard format like an ELF or a PE binary. So extract is saying, how do I get this firmware blob that is of unknown format into something I recognize, into code? And then analyze is what you're probably familiar with native reversing on Windows or Linux, where you just load it up into your static analysis tool and start reading code. These are the goals that I always seek when I'm enumerating firmware. So I want to answer these questions. What firmware exists on the device? And that's just a high-level list of everything with firmware. And then for each piece of firmware, I want to know where it runs and where it comes from. So where does it run is saying, basically, is this like pre-boot firmware? Does it run on the main CPU just before the OS? Or is this something like Wi-Fi firmware that runs in a completely separate, isolated chip with its own hardware, its own architecture maybe, and its own memory and connection to the main processor. And then I also, for each piece of firmware, want to learn how it's loaded, which ties into the obtain step that comes next. So I want to know where the system gets that firmware from so I can get it from the same place. So how can we answer these questions? There are a few ways. The first way is you can just open up your device and start taking photos of what's in there. Many pieces of firmware run on a separate dedicated chip, for example, Wi-Fi, flash storage. And if you can see that those chips are physically in the device, you know that the firmware exists. So that just sort of gives you a very high-level lay of the land And it's very easy to do. It's the exact same process regardless of operating system or specific technical details. In this talk, I'm going to be using Quest 2 as kind of an example, but these principles work on any device. You take out the main board of the device, the one with all the chips on it, take some photos of it. You can crank up the contrast like I've done at the bottom here to see the markings on them, or just look at them with a magnifying glass. And you see, if you're lucky, some devices don't have markings, but most devices will have some kind of part number or marking on the chip telling you what it is. One thing that you generally want to look for each device you find is something called a data sheet or a reference manual. That's the sort of official manufacturer spec sheet for the chip that says, here's what it does, here's the pinout, here's all the internals of it. Generally, you'll see a block diagram with, like, it has memory here, it has a CPU here. And it will usually tell you a few really important things. It'll tell you the architecture of whatever CPU is running in the chip. It'll tell you what bus the chip uses to communicate to the main chipset on the system. So, for example, a Wi-Fi card might be connected over PCI, or it might be connected over SDIO, and that's relevant to you if you're trying to compromise the Wi-Fi firmware and get back to the main chip. And then it'll hopefully also tell you how to update the firmware on the device, or where the device reads its firmware from. These pieces of documentation vary widely. If you're really lucky, you'll get a full reference manual, which will be hundreds and hundreds of pages detailing everything on the chip. It'll detail register maps, which we'll get to later, which are really useful for reversing. Most cases you won't get that because most vendors keep those under lock and key. But you will get usually just a few page data sheet with the high level specs of the chip, which is certainly better than nothing. If you're unlucky, you'll just get some press release confirming that the chip exists, but it won't really have much information. If you're in that final case, what else can you do? So this brings us to the second way to find firmware. And this is to look at the source code or the binaries that you do know how to analyze already. So you can start with the operating system because the main chipset on a phone or a laptop will necessarily be talking to everything that runs firmware, because otherwise there will be no reason for the firmware to exist. It will know about those devices and it will be able to communicate with them, and it might be able to tell you something about the firmware they run. So the example I'm going to use here is Linux. That's because most ARM devices, most embedded devices, and all of our meta hardware runs Android, which has a Linux kernel. This is not directly applicable to other operating systems, but the general techniques will apply. So the specific example we have here is excerpts from the kernel source code from the Oculus Quest 2. And you can see that kernel source code at this link down here. It's public as required by the GPL, and you'll be able to find that for basically any device running Linux. The first thing I always go to when I'm trying to enumerate firmware and I have kernel source code is I go to the device tree. That's this arch boot DTS directory. And that is, this part's gonna differ based on the architecture, but this part will always be the same. And then you can go in, find the vendor you want. The Quest 2 uses a Qualcomm chipset, so you go to QCOM here. And then Kona.dtsi in this case is the code name of the chip. And that you sometimes just have to search around until you find something that looks like your device. In each of these files, there is a bunch of just textual, human-readable code called a device tree. And a device tree is declarative. It's not like C code in that it does something. It's just declaring what hardware exists on the system, and the kernel uses that declaration to know what drivers to load, how to access hardware when it boots. Some newer ARM devices and most x86 devices don't have device trees. They dynamically fetch this configuration data from something like ACPI when they boot. But you can do similar things to parse out ACPI data and get the same kind of information. When you find a device tree, you'll see lots of entries like this. This is the entry for the Wi-Fi chip on the Quest 2. It's WLAN, wireless LAN. You can see the name and the compatible string here. both say Qualcomm CNSS, that stands for connectivity subsystem, and then a part number. The compatible string is really the thing to pay attention to. There's a lot of extra information down here. There's some register information, which again is useful to have once you get to analysis, but the compatible is really what matters for enumeration. And the reason that matters is because then you can go into the drivers directory of Linux. You can see what code, what C code, is used to talk to this device. So if you just take this string, search for it under drivers, you will find structures like this. And structures like this have a whole list of the different compatible entries that the driver is able to service. So in this case, we searched in drivers and we found net wireless CNSS2, main.c has a declaration that this driver, wireless CNSS2, is able to drive this WLAN chip. Once you get to the driver, what do you look for? This will require reading some code. If you're not proficient in C, don't worry. You don't need to trace it all through because there is a very easy shortcut you can use if you're just looking for firmware. This function called request firmware is a core Linux kernel function, and it'll be used by basically any driver which loads firmware directly onto the chip when the driver starts. At this point, I should digress a little bit to explain some common ways that firmware is loaded onto chips. Some chips have firmware built into them. So they have internal flash storage or even a ROM, just read-only memory, that contains their firmware, and just when you power them on, they start executing the firmware out of that. More chips, or at least more sort of external, smaller peripheral chips, don't have any ROM or flash inside, because flash is expensive and you don't want to put it in ROM because you might need to change it. So instead what they do is they just have RAM. They just have, volatile memory that gets cleared every time they shut off. And then when you turn them on, they don't actually start running right away. It's the job of the main kernel, your Linux or your Android, to load firmware into them and tell them, hey, this is the code you're going to be running to do your job. This is very, very common with Wi-Fi chips, for example. So this driver is no exception. You find this request firmware call, and that is where it's telling Linux, the driver is telling Linux, hey, get me the contents of the firmware for this chip so I can put it onto the chip and write it to the chip. The writing will be specific to the driver, but the getting from Linux is always done by this function. And the reason it needs a special API function instead of just being hard-coded in the driver or embedded is for two reasons. One, firmware is pretty big, and your kernel image will get really huge if you try to embed all the firmware in the kernel image directly. It would just get huge, and most of that would never be needed because you wouldn't even use most of the devices that you would have to build firmware in for. And the second reason is that firmware is usually not GPL licensed, so it isn't even legal to put the firmware in your Linux image directly. You have to separate it somehow. And so what Linux does is when it has a driver that needs firmware for a device, the driver always reads that firmware from a file on disk from user space. And because that's not something that's very commonly done in Linux, like you don't usually ever read things off the file system from the kernel because the kernel is for user space, not for itself. The file system is for user space. It's just hard to do, and there's not much support for it. And so there's this one function, request firmware, whose job is to sort of break that boundary in a safe way and go in and search several different places, actually, which I've outlined on this slide, for where that firmware exists. So the second argument here is the file name, and the driver will pass that file name in. And in this case, it isn't a hard-coded string. It actually comes from elsewhere, but if you do a little bit of tracing of the code, you can see it resolves to this string in black, QCA6390/m3.bin. And you can actually just look on the file system, because that's what the kernel does, and go through all the search paths, and on Quest 2, you'll find that exists in this directory, vendor firmware mount/image. If you get lucky and you find a driver that does load firmware every time it starts, then it's very easy to obtain the firmware. You've kind of done the next step for free because you can just read it off the file system. So that's a couple ways to enumerate firmware. And before we get to other ways to obtain the firmware, if you're not lucky like this, let's talk about the kinds of questions you want to answer for each piece of firmware that you find through either of these methods. So I like to fill out a table like this, if not, physically, at least in my head. And this answers some of those questions I posed initially. So up top here, these are 4 real chips in the Oculus Quest 2, and each one runs some firmware. And so I have compiled everything that I could find out that will be accessible to me as an external researcher. This doesn't rely on any internal data. About what each of these chips does, because you kind of need to know what the chips do and how they work to figure out which ones to target or whether they're even worth looking at. So the first one here is the flash storage. The interface to the chipset, I mentioned that before. It uses a protocol called UFS. Other common ones are eMMC, NVMe on laptops, you sometimes see for SSDs. This is the public documentation I could find. I could find a data sheet for this, but no full reference manual. And then I've sort of written down how I know that this thing runs firmware. For some of them, it's a little obvious, like any flash chip will have firmware, but it's nice to get a confirmation that that firmware isn't just squirreled away on some completely read-only memory with no way to get at it whatsoever. Because in that case, it's just probably beyond the capabilities of the average researcher to even get a copy of that firmware. So in this case, there was a reference in the product brief I found that said it supports field firmware upgrades. So we know the firmware is at least rewritable. And that also says, as an aside, the firmware actually exists in this chip. Unfortunately, this is probably the sparsest of the 4 in terms of documentation I could find. I don't know what CPU core it runs. I don't know where to find any firmware updates because it supports updates, but I couldn't find any in real life that have actually been deployed. But these other ones I had better luck. So I won't go through every single item, but this is the kind of table that is really, really useful to have just so you can look. And like looking through the file system on a high-level operating system, looking through a table like this gives you the lay of the land and lets you plan your next steps. Once you have this table, and you've picked a device to analyze, how do you actually get the firmware? That brings us to part 2, obtain. And like I said, sometimes it'll be very easy. If the driver loads firmware at every boot, you can just look through the paths on the file system, look for that firmware image from that the driver named, and I've put a list of common paths on Android and Linux here where you might find that. If you don't find a chip that has firmware loaded every boot, if it's like a flash chip, for example, or maybe a microcontroller, like a dedicated microcontroller that has internal flash, then that device will generally store its own firmware, and you will need to actually extract it from the device. So there are a couple ways to do that. The easy one is if you can find how the firmware is updated just during normal use, then you can reverse engineer that. And that'll usually be a binary that runs in Linux or Windows, and you can reverse engineer it in a typical way. And it will have access to a firmware update file, either embedded in it, or it'll know the URL to download one from. And then often these updates you can extract using traditional tools because they are running inside a high-level operating system. And then you have a copy of the firmware even if you can't read it off the device. If you can't do that, if there are no updates, for example, like that flash chip, then you have to go even further. And in that case, kind of your only option is to dig into the chip itself. If you have a reference manual, look for references to how to update or read the firmware, or how to run code on the chip even, and then try to actually just read it off the chip directly. And sometimes you can use a debug interface like JTAG for that. Sometimes the device will, if it's like an external peripheral, it'll have support for some standardized update protocol like DFU for USB. But in general, this is the hardest option over here on the right. And it's going to take a lot of work looking at one specific device before you can figure out a way to get at the firmware. That brings us to the end of part 1. We've talked about how to get the firmware, and these steps will leave you with a concrete file. You don't necessarily know what's in the file. In most cases, it won't be a standard binary like an ELF or a PE or something like that. But that's what the next part is for. So I will see you there.